In this lecture, we'll be doing problem solving involving uniform motion. This is one of my favorite sections. I think that the application problems are really interesting. Uniform motions means that the speed and direction of an object do not change. Imagine driving straight with cruise control on. We won't talk about instantaneous rate of change and taking off the cruise control until we get to calculus. The formula that we will be using for these problems is distance is equal to rate times time, or simply d equals rt. We're going to look at 4 different types of problems in this section. The first one involves one traveler making a round trip. A cyclist traveled at a rate of 24 miles per hour to visit a nearby town. The cyclist averaged 18 miles on the return trip. If the round trip took 4.9 hours, find the distance to the nearby town. It's really important to have a good picture so that we can understand what's going on. We know that's our first step for problem solving is to understand the question. So I have a cyclist traveling from his house to a town and then turning around and coming home. Although there's no proof by picture, we can see that the distance from home to town is the same as the distance from town back to home. Therefore, anytime you have one traveler making a round trip, you're going to write 2 distance expressions, one for going, one for returning, and then you're going to set them equal to each other. To get the distance expression, we need both the rate and the time, since distance is equal to rate times time. So let's start by talking about his trip going. The cyclist traveled at a rate of 24 miles per hour to the nearby town. So his rate when we're going is 24 miles per hour. The cyclist averaged 18 miles per hour on the return trip. So his rate here is 18 miles per hour. We need the time for both directions as well. The round trip took 4.9 hours. They don't tell us explicitly how long he biked either direction. So we're going to let the first one be X because I don't know what it is. They did tell us, though, that the total time was 4.9 hours. The time left for the return trip is going to be 4.9 minus X. We spent X hours going, so we need to deduct that from the total amount of time, which is how we end up with the expression 4.9 minus X. That means that the distance going is equal to the rate times time, which is going to be 24x, and the distance expression for returning home, again, is going to be the rate times the time. To get our equation, we need to set these two equal to each other. The distance going is equal to the distance returning. So that's 24x is equal to 18 times 4.9 minus x. To solve this equation, I need to distribute on the right. 24x is equal to 88.2 minus 18x. I notice that all my constant terms are collected on the right, therefore my variable terms need to move to the left. I'm going to add 18x to both sides. This gives me 42x is equal to 88.2. Last thing I need to do to solve for x is divide by its coefficient. X is equal to 2.1. I want to go back, reread the question, make sure I've answered the question they've asked. They want us to find the distance to the nearby town. When solving for x, we want to then look and see, well, what did x represent? X represented the time going, not the distance at all. So this is 2.1 hours. What we want to do, though, is actually answer the question and find the distance. ATQ is short for answer the question. Since the distance going is equal to the distance returning, we can plug this value of 2.1 into either of our distance expressions for x. I'm going to choose the one that looks easier, which would definitely be the distance expression for going. The distance is going to be 24 times x, which is 24 times 2.1. Our distance is equal to 50.4 miles. Again, anytime you have one traveler making a round trip, the distance going is equal to the distance returning. You want to write a distance expression for each direction, set them equal to each other. Now let's take a look at one traveler going in one direction. On the way to a ski weekend in Vail, Carlita drove 2 hours in a snowstorm. When it stopped snowing, she was able to increase her speed by 35 miles per hour and drove another 3 hours. If the entire trip was 325 miles, how fast did she drive when it wasn't snowing? Okay, so we have one person traveling in one direction. Part of the time she was driving, it was snowing, part of the time it wasn't. And she traveled a total of 325 miles. She drove a portion of that 325 miles while it was snowing, and then another portion when it wasn't snowing. The distance traveled when it was snowing plus the distance she traveled when it wasn't snowing, when it was sunny out, equals the total distance traveled. What we want to do is write a distance expression for when it was snowing, one for when it wasn't snowing, add those together, set them equal to 325. We're going to need a rate and time for each part of the trip. So she drove a total of, she drove just 2 hours in the snowstorm. So that's going to be the time in the snow is 2 hours. When it stopped snowing, she was able to increase her speed by 35 miles per hour and drove another 3 hours. So the time when it wasn't snowing, 3 hours. We need rates for each of these portions of the trip. It says when it stopped snowing, she was able to increase her speed by 35 miles per hour. What was her speed? We don't know. So we're going to call it X. But we know that when it stopped snowing, she was able to increase that speed by 35. So we'll take our original speed of X and add 35 to it. Now we'll write a distance expression for each portion. The distance when it was snowing is equal to the rate times time, which is 2x. And the distance when it was sunny is the rate times time, which is going to be 3 times x plus 35. These two distances added together will be our total distance. We get the equation 2x plus 3 times x plus 35 is equal to 325. I will distribute to solve. 2x plus 3x plus 105 is equal to 325. I have like terms on the left side to combine. 5x plus 105 equals 325. Since all my variable terms are collected on the left, I need to move my constants to the right. We'll subtract 125 from both sides. That gives us 5x is equal to 220. Last thing to do to solve, we'll divide by our coefficient. We get x equal to 44. Now that we've solved the equation, we want to go back, reread our question, make sure we've answered the question that they're asking for. They are asking us, how fast did she drive when it wasn't snowing? X, which is what we solved for, represented the rate when it was snowing. The rate when it wasn't snowing is 35 more than that. So let's answer the question. Find the rate when it wasn't snowing. The rate was equal to x plus 35. It's going to be 44 plus 35, 75 miles per hour. She was clearly making up for lost time. In our next type of distance problem, we have two travelers traveling in opposite directions. Two joggers start at the same time from opposite ends of a 6-mile jogging trail and begin running towards each other. One jogger is running at a rate of 4 miles per hour, the other running at a rate of 5 miles per hour. How long in minutes after they start will the two joggers meet? We have two joggers starting on opposite sides and running towards each other. The total distance traveled is 6 miles. Each jogger runs just a portion of this 6 miles. So this is very similar to the previous example, the one right before this that we did. The distance that the jogger 1 runs plus the distance that jogger 2 runs is going to be equal to our total distance. We want to write a distance expression for each jogger, add them together, and that'll be equal to our total distance of 6 miles. One jogger is running at a rate of 4 miles per hour. The other jogger is running at a rate of 5 miles per hour. It doesn't say anything explicit about the time, but we know we need time to be able to write our distance expression. Notice it says that the joggers start at the same time. If they start jogging at the same time, and they run towards each other, they're naturally going to stop when they meet each other. So they're starting at the same time and stopping at the same time. Therefore, the time that they're running is the same. We don't know what that time is. We're going to have to use a variable, but since they're the same, we can use the same variable. I'm going to use x for each time. You can never use the same variable for two different quantities unless you know that those two quantities are exactly the same. The distance ran by the first jogger is equal to our rate times time, 4x, and the distance run by our second jogger is our rate times time, 5x. The distance of the first jogger plus the distance traveled by the second jogger is equal to the total distance. We'll combine like terms on the left. 9x is equal to 6. To solve for x, we need to divide. We get x to be equal to 2/3. Let's go back and make sure we've answered the question. They asked us, how long in minutes after they start will the joggers meet? What did x represent? X represented the time traveled, so that's great. That's what they want us to find, how long, the time. But they ask for the time in minutes. Our time is currently in hours. How do we know it's in hours? Because our rate was in miles per hour. To answer the question, we need to convert 2/3 of an hour to minutes. And the way that we do that is by multiplying by 60, since there's 60 minutes in an hour. 2/3 times 60, they're going to meet in 40 minutes. Our last type of distance problem is two travelers, one chasing the other and trying to overtake or catch up. At 9 a.m., Katrina starts down an exercise path and walks at a rate of 4 miles per hour. At 9:30, Carla leaves from the same place and begins chasing her, catching her at 10 a.m. Find Carla's jogging rate. So I have these two joggers. They're starting at the same place. One's chasing the other, and they're going to stop when the second person catches up. Just like the very first example we did today, the distance of the first jogger is going to be equal to the distance of the second jogger, since they're starting at the same time and then going to stop at the same time. We want to write a distance expression for each jogger and then set them equal to each other. This will be Katrina and this will be Carla. We need rate and time for each. Katrina starts down an exercise path and walks at a rate of 4 miles per hour. At 9:30, Carla leaves from the same place, begins chasing her, and catches her at 10. Find Carla's jogging rate. That's our unknown. So Carla's jogging rate, we call it x. We need the time for each jogger. We see that Katrina started at 9 and Carla caught her at 10. So the time that she was walking, was 1 hour. Carla, however, starts running at 9:30 and catches up with Katrina at 10. So the amount of time she spent running was only a half an hour. And we need to make sure to keep the unit the same. Since we were talking about hours before, we need to write this as hours as well. I'm going to write this 0.5. The distance of our first jogger, Katrina, is going to be the rate times time. It's 4 times 1, or just 4. The distance traveled by Katrina is 4. Carla, her distance, rate times time, is going to be 0.5x. We want to set these two expressions equal to each other and solve. Get the equation 4 equals 0.5x. Solving for x, I'm going to divide by 0.5, which gives me 8 is equal to x. We want to reread our problem, make sure we've answered the question. We want to find Carla's jogging rate. What did x represent? X represented Carla's jogging rate. So we have answered the question. We just need to rewrite it with the proper units. Carla was running 8 miles an hour.